Okay, welcome to this video. We'll be looking at everything to do with vectors in the AS Pure Maths curriculum. So as you can see on the screen, some of the topics within vectors that we're going to be having a look at. We'll be having a look at vectors, geometric problems, magnitude and direction, and also position vectors and how to represent them. So as with all these videos, I'm just going to quickly show you how this channel works and how to use this video just in case this is the first time that you're seeing it. So when you are on one of these videos, if you click into the description, you can see the video there where I cover all of the AS Pure curriculum. And if you scroll down, you can also see all of the chapters. Now these will slowly be filling up until it has filled the entire AS Pure curriculum. So hopefully by the time that you are watching this video, all of them will be actually in the description and you can click and watch each chapter. If you click onto the video and click the link in the bottom left there, you can actually see all of the chapters that are within this video as well. So you can skip through and have a look at the pieces of that chapter that you are needing to have a look at for your revision. So that's how this video works. Hopefully that's useful and helpful. If you enjoy this video, please don't forget to like the video. Don't forget to share it with some of your friends. But with that being said, let's get started. Given that a equals 3i plus 4j and b equals I minus 2j, find lambda if lambda a minus b is parallel to the vector I plus 3j. Now straight away before we get started, you can see this time the coefficients of I and j are not equal. The coefficients of j in this particular instance right here are 3 times bigger than the coefficients of I. And we're going to bring that concept in the last step. Back when we were making them equal to each other, we're just going to think about how we're going to approach that. So we'll come back to that right at the end. So we've got lambda lots of a, and a is 3i plus 4j. So we've got lambda lots of 3i plus 4j, and then we're going to take away from that, you've got to be careful with this one, b, and b is I minus 2j. Now as we're taking it away, I'm going to put this one I minus 2j into a bracket. Obviously it doesn't matter if it's a plus between them, but when we're taking away, as we're taking away both of those, we don't want to forget to take away the negative 2, and otherwise we might only take away the I. So do be careful when you're doing takeaways, particularly when you've got more than one piece that you're taking away, that you put those pieces in a bracket just to avoid any mistakes there. So let's expand this bracket out and then obviously change the signs on that second one. So we have 3 lambda I plus 4 lambda j, and then we're going to take away I and also take away the negative 2, which makes it plus 2j. And there we go, that's all of those pieces listed out. Now again, we want to have a look at the coefficients of I and the coefficients of j separately, so let's join them together. So we've got the 3 lambda I, and we've also got the minus I, so we'll just put minus I, and then we've got plus 4 lambda j plus the 2j. And if we have a look at the coefficients that we've got here, we've got 3 lambda and also a negative 1 in front of the other one. A little bit hard to highlight that one there when we don't write the 1 in, but we know that that's a 1 and we can write that in as when we get to it. Now the coefficients of the other one, we've got 4 lambda being positive again, plus 2. So let's write these out and see what we've got. Now I'm going to do it like we did before. I'm going to change this in a sec because what I'm about to write isn't entirely correct, but I'm going to say, okay, well let's set these equal to each other. So we've got 3 lambda minus 1, and we'll set that equal to 4 lambda plus 2. Now technically what I've written there is not mathematically correct, and this is where we're going to have to look back towards this just here. And that's because we know that the coefficients of j are 3 times the size of the coefficients of I. And at the moment we've said that they're equal. Now in order to work around that, what we could do is we could say, okay, well this side here, we need to divide that by 3. You can do that, and that's absolutely fine. Ultimately you're going to get to this next step that we're going to write, but we could say, okay, well we need to divide that side by 3. Or what we could say is, okay, well actually the coefficients of I, we're going to have to multiply by 3. And if we make the coefficients of I 3 times bigger, they would then match the coefficients of j, which are already 3 times bigger, if that makes sense. So let's just times this side by 3, so we'll stick it in a bracket, we'll times it by 3, and then the coefficients would be equal. So let's go about timesing that by 3, so the 3 lambda would become 9 lambda, and the minus 1 will become minus 3. So 9 lambda take away 3 has to be equal to 4 lambda plus 2. And now we've got a nice easy equation to solve. So let's solve this over here. So let's minus 4 lambda from both sides. That would leave us with 5 lambda. And let's add 3 to the other side, and that's going to equal 5. So 5 lambda equals 5, so 1 lambda when we divide by 5 has to equal 1. And there's our final answer. Right, there we go. So that's how we're going to approach these questions, and it's all about looking at the coefficients and making this little equation and making them comparable. So if the coefficients, or if there is only one letter, then we need to eliminate one of the other letters or one of the other directions. If the coefficients are equal, we can set them equal to each other and solve it. And obviously then if the coefficients are different, so we have something like I plus 3j, or maybe you could have, I don't know, 5i plus j, you would actually have to multiply one of the sides to obviously make them equatable, and then obviously you can do your equation from there. So this one says we've got 3 vectors. We've got A, which is p over minus q, we've got B, which is q over p, and C is 7 over 4. Given that A plus 2B is equal to C, find the values of P and Q. Well, first of all, let's work out what A plus 2B is. So we've got A, which is P over minus Q, and we're going to add to that 2 lots of Q over P. And it says that that is equal to C, which is 7 over 4. Now, first thing to note here is obviously we have 2 unknowns. We've got a P and we've got a Q. And there's a little hint in that, and whenever we do have 2 unknowns, sometimes we may have to look at simultaneous equations. There's a little bit of a hint in here that we may have to involve another topic within this question. So let's have a look. Now we need to do 2 lots of P and Q. So we've got P on the top, and let's just add together that top line there, but also timesing that right vector there, the 2 lots of P over Q by 2 at the same time. So we have P plus, and we're going to have 2 Q's, as we're going to multiply that one by 2, and that's going to equal the top number over there, which is 7. Now if we have a look at the bottom line, we've got negative Q plus 2 lots of P, which is going to equal 4. So negative Q plus 2 lots of P is going to be equal to 4. And there we go, we've got 2 equations, both with P and Q in, and we can use simultaneous equations to solve that. Now, just for the purpose of making this look a little bit nicer, what I'm going to do is I'm going to swap over the Q and the P just to make sure that they're aligned with our simultaneous equations. You certainly don't have to, but I think it looks a bit nicer when we line them up in the same way. So rather than writing minus Q plus 2P, I'll write 2P minus Q. So let's get rid of that, and we'll write 2P minus Q. There we go, so we've got our simultaneous equations. Now in order to solve our simultaneous equation, obviously we need a similar numbered coefficient with either P's or Q's. I tend to like to make the second one the same, so I'm going to times the bottom equation by 2, so that we have 2Q for both of our equations. So we'll times that one by 2 and rewrite it. So let's have a look. When we times that by 2, we get 4P minus 2Q, and that now equals 8. There we go, so we've got our 2 equations. We can forget about the one in the middle. In fact, let's just get rid of that one. Okay, we lost the Q there. Let's get rid of that. There we go. And we'll solve it from there. Let's move this up just above. There we go. And we have different signs in these simultaneous equations, so we'll add them together. And let's have a look. We get 5P. The 2 and the minus 2Q obviously disappear there, they cancel each other out. And we have 7 plus 8, which is 15. And there we go, nice and easy to solve then. P is equal to 3, 15 divided by 5. Now we've got our value of P. Just like with normal simultaneous equations, we're just going to substitute that back into one of these equations up here. So we'll sub it into the top one. So if P is 3, we get 3 plus 2Q is equal to 7. We can subtract 3 from both sides. So 2Q is equal to 4, and divide by 2, Q equals 2. And there we go, we've solved that question. Just highlight our 2 answers there, because we've got P equals 3 and we've got Q equals 2. So something a little bit different there. Obviously we didn't write it in our normal vector way with our i's and our j's, but just goes to show you that we can actually have these questions involved with normal column vectors as well, with something a little bit different with simultaneous equations there. Now with this question here, we're going to have a look at the magnitude, which is essentially the distance that 2 vectors actually travel when we combine them together. And we're going to have a look at drawing that down and writing a little sketch of them to see what it looks like. So as always, grab a piece of paper, grab a pen, make some notes, and we're going to start with this question on the screen. So it says, given that A is 3i plus 4j and B is negative 2i minus 4j, and we're going to find two different things here. Now already you might have noticed there's a little bit of new notation to write, and that is this bit here where we have it says find A, and it's between these two lines. Now those two lines just mean the magnitude of whatever's inside it. So this means the magnitude of A. And if we visualise what A would look like, I'm going to have a look at what the magnitude actually is in terms of a visual picture. So for A, it goes 3i and 4j. Now that means it goes 3 across, if we just pick any particular direction, and then it goes 4 up, obviously not drawing this to scale. So that's what our vector looks like. Now in terms of our starting point, we started over here and we finished up there. So our vector has actually gone in this direction that I'm drawing in with that green line. And as you can see, that forms a right-angled triangle. Now the topics that are going to be involved in this, obviously when we're looking at right-angled triangles, we can have either Pythagoras or potentially we could use some SOHCAHTOA. And if we want to find the length of that line, which is what the magnitude is in this case, the actual distance that we've travelled by going 3 across and 4 up, we're going to use Pythagoras to work that out. So we can draw a right angle in if we want, but ultimately if we're going to use Pythagoras to find this magnitude, we just need to go about using Pythagoras' theorem. So for part A here, we have a length of 3 and a length of 4. So we're going to do 3 squared plus 4 squared, and then we're going to square root our answer. Now, rather than doing this in 2 steps, let's just stick our square root right over the top, and there we go, we can stick that straight into the calculator, and we get the answer of 5. So the magnitude of the vector A is 5, or in other words, it travels an actual distance of 5 units, whatever those units may be. Now, for part B, it says find the exact value of, and that exact there giving us a hint that our answer is going to be in surd form, which we'll hopefully see in a sec, and it wants us to find the magnitude of 2a plus b. Now, it's completely up to you. If you want to find 2a plus b by writing these in column vector like we went over in part 1, you can do, or you can just use your sort of mathematical logic here to get two a's together. So 2 lots of a, well if we deal with the i's to start with, we'll have 2 of these 3i's, that gives us 6i, and then we've got a b that we're going to add to that, and in that we've got negative 2i. So we've got 6i, take away 2i, and that's going to leave us with 4i, so that's going to go 4 across. Then we've got to do the j's, so if we do those separately, we've got 2 lots of the 4j, which is 8j, and then we're going to add to that the minus 4j over here, and that leaves us with 4j. So we have 4i plus 4j. So that is our vector 2a plus b. Of course, we're going to find the exact value of the magnitude of that vector. So for part B, we're going to take the same approach and we're going to use Pythagoras again. Again, you could draw a sketch of this 4 across 4 up, but once you get your head around this, hopefully you can avoid potentially having to draw some of these sketches when they are slightly easier like these ones here. So in terms of using Pythagoras, we know that goes 4 across, so we'll do 4 squared, it goes 4 up, so we're going to do another 4 squared, and we're going to square root our answer. Now 4 squared plus 4 squared is 32, so we have the square root of 32, and to be fair, that is the exact value there, although when it comes to surds, we should always look to simplify them wherever possible, and considering you have a calculator for these questions, it's easy enough just to type it into the calculator, and it's 4 root 2. There we go, it's root 16 root 2, root 16 goes down to 4, so 4 root 2 there being our final answer, 4 root 2. So there we go, that's what we mean by the magnitude of a vector. Okay, so on to our last little bit here. It says in a triangle, PQR, P to Q is 4i plus j and P to R is 6i minus 8j. Find the size of the angle, QPR, in degrees to 1 decimal place. And it also wants us to find the area of the triangle. So let's go about drawing this. Now let's start with P, as both of these vectors are going from P. So let's call this point here P. Now the first vector there is going 4 across and 1 up, so let's just imagine that 1, 2, 3, 4 across, 1 up. So let's just imagine it's here. There we go, and we'll call that point Q. Now to find point R, that's going 6 across and 8 down. So let's do it again, 1, 2, 3, 4, 5, 6, and then 1, 2, 3, 4, 5, 6, 7, 8. Right, okay, there we go, not to scale, but just to give us a general idea of what it looks like. And that is our point R. Now let's join these all together. So P to Q Q to R, and R back up to P. There we go. So this wants us to find the size of angle QPR. So QPR is just over here, and again, let's call that theta. There we go. And it wants us to find it in degrees to 1 decimal place. Now, in order to find an angle within a triangle like this, as this is not necessarily a right-angled triangle, we actually don't know, we can't really tell just by looking at it like that, we would need to use the cosine rule or potentially the sine rule. So we are going to involve another topic here, and again, things like the sine and cosine rule, I'll link in the description below, just to make sure that you're nice and clued up on those if it's something that slipped your mind. So looking at this then, what sizes or what sides can we find the length of, or in other words, the magnitude? Well, we can do that for P to Q, and we can do it from P to R. So let's start with one of them. Let's go for P to Q to start with. Now here's our little notation here. We've got 4i plus j, so we've got a distance of 4 and 1. So for P to Q, and let's write it in proper vector notation, let's find the magnitude of PQ. So we've got 4 squared plus 1 squared, and we're going to square root that. So 4 squared is 16, plus the 1 is 17, so we have the square root of 17. There we go. So the square root of 17 for our first one. For P to R, we have 6i minus 8j, so let's find the magnitude of P to R. Well, that's going to be 6 squared plus the 8 squared, and we're going to square root that again. Okay, so let's stop doing these in our head, let's get them typed in. So 6 squared plus 8 squared, square rooted, there we go, gives us the answer 10. One that we should know actually there, 36 and 64. So there we go, there is the length of 10. There we are. Now, have we got enough information to find the angle? Now, if we had the length Q to R, we could actually use the cosine rule, okay? But we don't have the length Q to R just yet. But actually looking at our diagram, it's not that difficult to find. There's two ways that we could do this. We could either take the vector P to R and take away the vector P to Q, or we could do it vice versa and just be very careful in the direction that we're going in. Or to be fair, we could just use a bit of a logical approach. Now, to get from P to Q, we've had to go 4 to the right, if you remember drawing those dots. And we've got an extra 2 dots across to get from Q to R. So in order to do the vector from Q to R, we could actually just take this logical approach. If we've gone 4 across from P to Q and an extra then 2, obviously because we've gone 6 across to R, then we know that must have been 2i across. And we can take the same approach going down. From P to Q, we went up by 1, but from P to R, we went down by 8. So if we went up by 1 to get to Q, but down by 8 to get to R in total, that's going to have to go down by 9. So minus 9j. Now, you may not like that logical approach, so you don't have to use that. You can actually just take one of the vectors and subtract the other one. If you have a look, and let's just highlight it, the vector P to R, 6i minus 8j. If we do 6i, take away the 4i in the previous one, that leaves us with 2i. And if we do minus 8j, take away the 1j, that also leaves us with minus 9. So you can just take that approach as well, but I do think it is worthwhile just thinking about logically why you get the answer, and not just simply taking one away from the other and not really understanding why. But it is a nice little shortcut there to actually get these vectors when you're trying to find them. So there we go, we've got enough information now to also find the magnitude of Q to R. And we can take the same approach, just using Pythagoras again. So from Q to R, we can do the square root of 2 squared plus 9 squared. 2 squared is 4, 9 squared is 81, so that is 85, or the square root of 85. Right, so we've got all the side lengths now. All we need to do is go about actually finding this particular angle. So let's get rid of all of this working out. Now obviously we need our magnitudes there, so we'll have to leave those, or we can just draw that onto the diagram now, root 85, and we'll get rid of all that working out. There we go, so let's get rid of all of that and just work with our diagram. Quite a lot working out up to this point, but to be fair, we've only had to use Pythagoras a few times, so nothing too bad. So to find the size of that angle, we obviously need to know the cosine rule, and obviously in this particular instance, we're looking at the cosine rule for the angle. So the cosine rule for the angle is going to be cos theta, and you do need to know these well, and we're going to do b squared plus c squared minus a squared all over 2bc, or whatever variation we're looking at. I'm treating theta as being our big A in this case. But let's go for it. 10 squared plus, we've got root 17 squared, which is just 17, but I'm going to write it in anyway, just to make sure we don't get confused with any of this. And then we're going to take away the root 85 squared, which again is just 85, but we'll write it all in as normal. And that's all over 2bc. So 2 times 10 times root 17. Now I'm going to do a little bit of a cheat here. Before I type that calculation in, I am just going to press Shift Cos and do the inverse straight away. So just a little step that I am skipping here. Rather than writing it all down, I'm just going to do the inverse straight away. So on the top then, 10 squared plus root 17 squared plus root 85 squared all over 2 times 10 times the square root of 17. There we go. Close your brackets on your calculator, and we should, let's have a look, if you type it in correctly, we should get 67.16. So there we go, our angle to one decimal place is going to be 67, it's 0.16, so 67.2 degrees. And again, just remember, I have skipped a step in my writing there just to reduce the amount of working out that's on our screen. So there we go, there is our angle, and the second part is asking us to find the area of the triangle. So we've got another bit of trigonometry coming in here. We're going to have to use half AB sine C. And just as a little tip here, I'm going to keep the original answer on my calculator, so the 67.16634.582. So if you're not going to keep that on your calculator, do make sure you have written down the full number there, because we don't want that to affect our area and part B. So for working out the area, we're going to do half AB sine C. Again, we now know the angle here, so we can get rid of theta. Oh, not the whole triangle there. We might be able to do it. There we go. And we can put the angle in. So 67, in fact, let's just write the whole angle in. 67.16634.582. And now we can do half AB sine C. So the area is going to be a half times our two adjacent sides there, so 10 times root 17 times sine of this angle, 67.16, and the rest of those decimals, I'm just going to use the answer button on my calculator. So 0.5 times 10 times root 17 times by the answer, and there we go. Obviously typed it in wrong, so we're going to have to go right back to the beginning and just retype that in just to get that full angle back. In fact, no, we've written it down, so we can actually go ahead and do it, and there is the benefit to writing the full angle down. If you do type something in wrong in your calculator, like I have just done, then you can go back and you can type it back in without having to worry about getting that full answer back on your calculator. So 67.16634.582. There we go, and there's our answer, and that comes out as 19. There we go. Obviously, we don't know what the units are here, so we could say 19 units squared, but we're not going to worry too much just here when we're practicing on this one, but 19 units squared, whatever they are. Okay, so let's highlight that off, and there is our final answer. So just making sure that you're very careful with these. Obviously we had to involve the cosine rule to find an angle, we had magnitudes, we had obviously that bit of logical thinking to find that missing vector there from Q to R, and then also we had using half AB sine C, or our area of a triangle formula as well.
Okay, so when it comes to geometric vector proofs, a lot of the proofs are very similar to those we've learnt at GCSE level. So I'm going to go through this one quite quickly, assuming that you have knowledge of vector proofs from GCSE. Again, if you're not sure, you can always check out the full video in the description on that, but otherwise we're going to have a look at this question. So it says OAB is a triangle, O to A is A, and O to B is B. It says the point M divides O to A in the ratio 2 to 1, and M to N is parallel to O to B at the bottom. So first things first, we should label those on our diagram. So O to A, and we'll put the direction in, is the vector A, and O to B is the vector B. Now what we can do is we can split that up into the ratio. So O to A was 2 to 1, so this is going to be 2/3 A for this part, and this part will be 1/3 A. Now for the first part of the question, it says express the vector O to N in terms of A and B. So we want to get from O at our starting point here all the way over to N. So we're going to look at some vectors to start with. Now moving from O to A is easy enough, but A to N is a little bit trickier. So we're going to need to look at this and think about the fact that M to N is parallel to O to B. And looking at O to B, which only has a B in its vector, means that M to N must be a fraction of B, so it won't have any A's in. That should help us to work it out. So the first vector we're going to find here is A to B. So if we look at the vector A to B, that means we're going to have to go from A down to O and then over to B. So that is going to be minus A plus B. And just to make that look a little bit neater, we'll write that as B minus A, just so we reduce our amount of negatives. Now on to the next part, we can think about how we get from A to N. Now we don't know what the ratio of A to N and N to B is, so we're going to have to use some algebra, or of course you can use lambda in this instance, but I'm going to use the letter X. So we're going to say that A to N is some amount of B minus A. And we're going to find out what X is. Now if that is the case, let's have a look at M to N and think about potentially what that fraction will have to be. So to get from M to N, we know that that is going to have to be a multiple of B. So if we were to expand this bracket, we would have to do A to N plus M to A. So M to A is already drawn on the diagram, that is 1/3 A. That gets us from the point M to the point A, and then we're going to add to that x lots of B minus x lots of A. Again, that's just the vector above here, but just expanded, so that would be xb minus xa. Now we need to just have a look at this, look at those A pieces. We've got 1/3 A minus xa. Now obviously in order to eliminate the A's there, that means that x has to be 1/3. So x will have to be 1/3, and that allows us to put our x in, so M to N is going to be 1/3 B. Obviously the A's there have just cancelled each other out. So now we have the vector M to N, we can get the vector O to N. So now we've got M to N, we need to think about how we get from A to N. Okay, so that's going to allow us to go from O to A using the vector A, and then down from A to N. Okay, so A to N we have already worked out. And if we just highlight that so we remember where it was this vector here, xb minus xa. Of course we already know that x is 1/3, so we could write that A to N is equal to 1/3 B minus 1/3 A. And again, let's just write that a little bit clearer there. So that is 1/3 B minus 1/3 A. Okay, so that is A to N, and obviously we want to get from O to N. So O to N, if we were to write that in terms of the vectors, O to N is going to be equal to O to A plus A to N. There we go. Now we have both of those vectors. O to A is just the letter A, so that one is going to be A, and we're going to add to that A to N, which we've just worked out, and A to N is 1/3 B minus 1/3 A. There we go. And if we simplify all of that, that is going to be, let's just highlight what we have. We've got the A and minus 1/3 A, and that is going to go down to 2/3 A, which we can write first. So 2/3 A, and then we also have the 1/3 B, that's positive 1/3 B, so plus 1/3 B. So there we go, that is our vector. We have 2/3 A plus 1/3 B. Now we'll highlight that because that's finished, but of course you could factorise out 1/3, it doesn't ask us to, so it is fine to leave it in that form, but our final answer there is 2/3 A plus 1/3 B. Now for part B, it says show that A to N, N to B is in the ratio 1:2. So we're going to need a little bit more space for this, but in order to do this, we're going to think about some of these vectors. Now if it is in the ratio 1:2, then we just need to think about some of these vectors that we've got, and we've already worked out the A to N, and we'll write that down just up here so we don't lose it, because I'm going to have to rub some of this off the screen. But A to N was equal to 1/3 B minus 1/3 A. So there we go, and we can also think about the overall vector of A to B, the full length of the line. Now A to B we wrote down at the very start, and that was B minus A, and we've got that just over here. So we're going to need that vector A to B, and we're going to need this vector A to N. and then we can think about the other portion of that and why it's going to be in this ratio. So if we get rid of some of this working out, and there's quite a lot of it, so let's just get rid of all of that. And now we can go about actually tackling this question. So we've got that a to n is 1/3 b minus 1/3 a, and the full vector a to b is b minus a. Now you can already see that a to n, if we were to factorise that, would be 1/3 of b minus a. So if the full line is b minus a to n is only 1/3 of that, then n to b will have to be 2/3 of the line, so that would be 2/3 of b minus a. Now ultimately what we have shown there is that a to n is 1/3 of the line and n to b is 2/3 of the line. So as a ratio of a to n, n to b, that has come out as a fraction which would be 1/3 to 2/3. And that is obviously can be divided by 1/3, and that is the ratio 1 to 2. So there we go, we have shown that that would have to be the ratio 1 to 2 by looking at the full length of the line and the first part of the line. Okay, so when it comes to modelling with vectors, the questions are quite in depth. Now some of the other questions that we've looked at are quite similar to this, but we're going to have to draw some bearing diagrams for this. So it says a man leaves a starting point O and walks 15 kilometres on a bearing of 120 degrees to reach A. So if we imagine that O is just over here by our question, and obviously with bearings we need to draw in our north line, then we need to think about what 120 degrees would look like. So it's a little bit past 90 and it would go down to here. We would then reach point A, so we should label this up and again draw in another north line. So this is going to be point A, and we've now got that this is 120 degrees. If we move on to our next piece of information, it then says from A he walks 9 kilometres on a bearing of 240 degrees to point B. So if he's standing at A, he's going to go 240, which goes past 180, but not past 270, so it's going to go somewhere down here. Now at the first point it said he walked 15 kilometres, this one was only 9, so it's not going to go too far, but again we are just drawing a sketch. So again, let's just write that in, make sure we have this all labelled nicely, and also we're going to want to show that that right there was 240 degrees. So we're getting there with our diagram. It then says in the final part of this that he then returns directly to O. So he's down here at point B and he's going to walk straight back to O. So as you can see, this has created a triangle. We could also put a north line in at B, but we'll see how much of this we're going to need in the question. Now looking at what we have here, we want to find the position vector O to A. Now that can also be phrased in a slightly different way. It could say the position vector of A relative to O, which just means starting at O and going to A. So if we're going to work this out, we need to think how we're going to get there. So in order to do a position vector, we want to know how far it's gone across and how far it's gone down. And if we think about that in terms of from O, we're going to go across, and let's do this in a different colour so we can see this. It goes across from O over to this north line, and then it's going to go down. Now by doing that I have created a right angled triangle. So we can use some trigonometry to figure out these lengths. So if I move this 15 kilometres and we just put that above the line, as that is going to be in our way a little bit, so we'll put that just below this line just here, as that was the 15 kilometre line, and now we can go about working this out. So for that particular line going across, we can use some SOHCAHTOA. Now that right angled triangle does split that 120 degree angle. As we are going perfectly to the right there, then that is going to be 90 just above it, which means that just in the triangle here, that would be 90 plus 30, which would make that add up to the 120. So if we use SOHCAHTOA, we can work out both of these lengths, and we'll write that using then I and J. So the length across the top of the triangle, we would use cos for, as we have the hypotenuse and we're looking for the adjacent. So for this line just here on the top, we would actually do 15 cos 30. Again, you can slow this down a little bit and think about why it's 15 cos 30 there, but hopefully you're happy with your SOHCAHTOA. Onto the one going down, this is the opposite, so we will use sine as we already have the hypotenuse. The hypotenuse again is 15, so that would be 15 sine 30. So the distance is there, we could just type into our calculator. Now of course we're going to write this as a position vector, so for part A here, we would want to say that it is going to be 15, and then going across was the cos 30, so 15 cos 30, we can put that in a bracket if you want, I, and then we're going to take away from that as we are going downwards 15 sine 30. So that's going to be 15 sine 30, and that is going to be a j. So if we type that into our calculator to work it out, 15 cos 30 to 1 decimal place comes out as 13.0, and that is going to be our vector I, and then we're going to go down by, and if we type in 15 sine 30, that comes out to 1 decimal place as 7.5, obviously, and that is going to be our vector j. So that is the first part of our question there. We have found the position vector O to A. Part B here asks us to work out the magnitude, but this time it asks us to work out from O to B. So if we go over and think about our triangle and think about how we would work that out. So if we're trying to work out the distance from O to B, we are looking at this line just here, and we want to work out the length of that line. So to work out the length of that line, we could use either sine rule or cosine rule. So if we look at what we have in the triangle at the moment, can we work out anything in this question? So we need to have an angle. Now what you will see in the green triangle that I have drawn, we already had a 30 degree, a 90 degree, and therefore this angle in the green triangle would have to be 60. And of course that bearing around A has to fully add up to 360. Now there's 240 on the outside, 60 just in here, so this angle inside the triangle will have to be 60 degrees as well. Now we can't actually get any of the other angles, but do we have any pairs of opposites? Do we have anything that we can use potentially with the cosine rule? Now we don't have any pairs of opposites, but we do have the angle, and we have the 15 and the 9 just next to it. So we'll be able to work out the length of that line using the cosine rule. So for part B here, to get the length of that line, O to B, which we can just say OB, so OB, we'll put that in brackets because that's squared, is going to be equal to A squared plus B squared, so 15 squared plus 9 squared, minus 2AB cos C, or depending on which way you write your cosine rule, but minus 2 times 15 times 9 cos 60. So if we type that in, we get that OB squared is equal to, and all of that simplifies down to 171. So there we go. To get OB, we would just have to square root our answer. So OB is going to be the square root of 171, which comes out as, and if we do it to 1 decimal place again, it comes out as 13.1 kilometers. And there we go, that is the length of O to B, or in this case we are calling that the magnitude of O to B. Again, they mean the same thing when we're looking at this vector. Okay, so if we move on to part C here, it says find the bearing of B from O. So if we're looking from O, to get down to B, we already have part of that angle. We have the 120 degrees leading up to the start of our triangle. The only thing that we're missing here is this angle here within this triangle. So if we call that theta, and we'll think about what we could use here. So in order to get the angle, again, we could use sine rule or cosine rule. Now let's label on this 13.1. Actually, instead of putting 13.1, let's put the exact value in, because we did round part B, so that is the square root of 171. Now, in order to work this out, let's just have a quick look and see if we can use the sine rule. And for this particular question, we have the length opposite the angle we're looking for, and opposite that root 171, we have the angle of 60. So for this question here, we can use the sine rule, so let's use that as it's a little bit quicker. So we've got sine theta, we're looking for the angle, so angle on top. Sine theta over 9 is going to be equal to, let's have a look, sine 60 over the square root of 171. Now if we rearrange that, multiplying both sides by 9, we get that sine theta, and let's just type that in on the top, 9 sine 60 over the square root of 171, comes out as 0.59. There's a few more decimals here, it is 6, but then there's a few more decimals. And in order to work this out now, we need to do the inverse, so we'll do sine minus 1 of the 0.59, again putting the full digits in there using your answer button, and it comes out as, and let's do it to 1 decimal place, that comes out as 36.6 degrees. So we've worked out the angle in the triangle there. There's quite a lot going on the page, but that angle just there is going to be 36.6 degrees. Now obviously the bearing is the overall angle, so we need to add that onto the 120. So to get the final bearing, we would do 120, and we've kind of run out of space here, so I'll put it over to here, 120 plus the 36.6, and that comes out as 156.6 degrees, and that would be our final answer there for part C. Okay, so on to our final part of this question, we've got part D. Now in order to answer this, we're going to need to get rid of a lot of this information, but it is very similar to part A. So if I get rid of a lot of this information, let's have a look. Okay, so now we've got a little bit more space, let's think about this diagram. Now we've still got quite a lot drawn on the diagram there, but if we just draw a little sketch of this triangle just to the side, and we'll imagine again that this is O, this is A, and this is B, and we can think about obviously what we need to do here. Now in order to get the position vector from O to B, again we're going to need to draw in a right angle triangle. So if we go across from O and then down to B, again it would form this right angle triangle. And all we need to do is think about one of the angles within that triangle, and we should hopefully be able to use SOHCAHTOA again to find our distances. So for this particular one here, let's not forget we already have the length of the hypotenuse, and that was the square root of 171. We then also need to figure out an angle, and if you look back in our diagram, we actually have this angle here. So for that particular angle there, obviously our right angle triangle goes just above it, but we already know that that's an angle of 30 degrees, plus we have the 36.6 degrees, so the full angle within the triangle just there would have to be 36.6 plus the 30, which comes out as 66.6. So the angle within the triangle, and again you could always just draw that triangle separately to the side, but what we have is a length of 171, and we have an angle of 66.6. Now what I'm going to do for this one, I'm just going to round that to 67. You could keep it accurate to be fair, and you could write 66.6. Either one of those is absolutely fine. So in order to work through this, again we're going to write our vectors in terms of I and j. So to get from O to B, we would have to do, let's just have a think about this. For I, we want to work out this length just here. Now in regards to the angle, we have the hypotenuse and we are working out the adjacent, so we're going to use cos. So we're going to do the hypotenuse, which is the square root of 171, cos of the angle, which is 66.6. And if we type that in, the square root of 171, and then cos 66.6 comes out as 5.19. So that is going to be 5.19. So we'll write this in, and we'll just write it straight in as we've done the working out just on the diagram there. So for I, we would have, and let's just put it below where I've drawn the OB, we would have 5.2, if I round that to 1 decimal place, I, and then we are going down, so we're going to minus j here. To work out j, this length just here, again, we are going to use sine. So for sine for that one, we can use root 171 sine of the angle, so 66.6. And if we type that into our calculator, root 171, and all I'm going to do is get rid of cos, replace it with sine, and press equals, and we get 12.00. So for that one there, again, we'll just write this in, so that would be 12.0 to 1 decimal place, and that would go with our j. So there is our answer, 5.2i minus 12.0j. Of course, that could come out slightly differently if you use rounded answers. So if you had used the rounded version of root 171, which came out as 13.1 kilometers, or if you used the rounded version of 66.6 and you instead used 67, you would get a slightly different answer. But that is an overview question that covers a lot of modelling with vectors.
Okay, that is the end of the video. I hope you found that useful and helpful. If you did, please don't forget to like, don't forget to comment, don't forget to subscribe to the channel, and I'll see you for the next chapter.